Thank you for the invitation for presenting here today. So I'm gonna speak a little bit about modular type functions and some applications in mirror symmetry. So my idea is to generalize modular forms in some sense. I will try to explain. And so a brief outline of what I'm going to speak today. So first, I'm going to talk about the Gmcd project, which is a bigger project idealized by my advisor, Hossein Movazati. And the idea is to try to create these modular type functions for many examples. So I speak about that and give very briefly an example in the elliptic curve case. After that, I'm going to speak about what happens in the closed string case, which was already done. And in my work, I made the same thing for the open string case, which is a bit different, but not very much, but it's a nice advance. And in the end, I'll try to give explain why are all this stuff related with mirror symmetry, and I mean try to explain why some numbers are appearing and etc. So let's begin. So Gmcd is Gauss-Manin connection in disguise, and it's a way to generalize the concept of modular forms, but more specifically quasi modular forms. Our idea is some kind of a geometric idea. So we are going to consider the modular space of n-dimensional varieties. So you start with some kind of family of varieties here, and you consider the algebraic cohomology of these spaces, which is a sheaf over S, and then you consider pairs of varieties in this family and a basis for the algebraic cohomology. So this is basis for algebraic cohomology. So we consider this, and after this, what we get is we can consider the moduli space of these pairs here, and this is going to be a quasi-affine space, at least in the examples we considered. It's not gonna, I mean, we actually don't know what happens in general, but in the examples I'm considering, this is going to be quasi-affine. And so we have the moduli space of these pairs, and we can take some coordinates for it. So this is the first step. After this, we can compute the Gauss-Manin connection of this family with respect to this basis. So we have this basis, which is actually, I mean, so what we have is kind of a section, I mean, k sections of the algebraic cohomology sheaf, and then we can compute the Gauss-Manin connection with respect to this basis here, and we can do it explicitly, actually, because we have this space here explicitly, this moduli space. And after this, we find what we call a modular vector field, which gives differential relations among these coordinates. So we have coordinates for these spaces, and then using the Gauss-Manin connection, we can compute a vector field. Recall that this is quasi-affine, so this vector field actually is very explicit. And this vector field will actually give us differential relations among the coordinates, right? So we actually will get a system of differential equations, and if we solve these differential equations, we are going to get some kind of Q expansions. And if you recall quasi-modular forms, we have a differential equation, like a system of differential equations relating like the Eisenstein series, and that's what I'm going to explain in the elliptic curve case. And this vector field actually will give rise to a kind of a domain, which is going to be like a generalization of the upper half plane in the case of classical modular forms. So let's try to explain what happens in the elliptic curve case. So we are going to consider elliptic curves and a basis for the homology. And very important detail I forgot to tell, we not consider any basis, right? So we have two important properties we need to consider. So this basis has to respect the Hodge filtration. So of course we have a Hodge filtration in the De Hooch homology, and the basis has to respect this Hodge filtration in the sense that, for example, in the sense that if we consider, for example, in this case, alpha should be on F1, right? And omega should be on F0, but not on F1. And that's what that's what we do in general, right? So the first element is on Fn, and then we consider elements on Fn till we have no more dimension for it, and then consider elements on Fn plus 1 which are not on Fn, and etc. Right? So actually what we are doing is that we are considering somehow this identification here. Right? And I mean, we are taking a basis which respect this identification. Yeah, so that's the first thing. And the second thing is that we ask the intersection product to be constant. So for example, in this case, we ask the intersection product of alpha and omega to be 1. And in the other cases in which we have more elements, we choose a matrix here for the intersection product. So we want to control this intersection product. So actually we are considering the modular space of bases elliptic curves and bases with these two conditions, right? And this is very important. So after this, we can compute this modular space, which actually is going to be dimension 3. I'm going to write it here. So this is going to be T2 cubed minus 27 T3 squared. So the discriminant should not be should be different from 0. And let me explain how this identification is made. So we start with elliptic curve given by some equation like this. So 4x cubed minus, let me write this way. So x minus t1 cubed minus t2 x minus t1 minus t3. So, and we have alpha be this and omega this one. So this is how we identify. So we take a curve, any elliptic curve can be written in this form, and then we can write take these two forms to be alpha and omega. Oh, notice that I could take this t1 off because I don't really need this t1 here, but if I took it out here, I would have to put it here in omega. So it's just the same thing. And that's why you have like 3 dimensions. I mean, 1 dimension is for the elliptic curves varying, and the other 2 dimensions are for choosing a holomorphic form, and the other one for choosing a non-holomorphic form. So that's kind of expected, the expected dimension. So we have this. The first thing is that we have this modular space, and how we get, I mean, we recover modular forms. So, I mean, people should be already like realizing that these TIs are related with the Eisenstein series, and I mean, that's true. What happens is that we can compute the Gauss-Manin connection explicitly in this case, and after that we can consider the following fact. There is a unique vector field R such that the Gauss-Manin connection applied to the form alpha is minus omega, and the Gauss-Manin connection applied, I mean, to omega is 0. So we can show this by computation, and the point is that this vector field R here is exactly okay. So this is a vector field on T, right? Because the Gauss-Manin connection is a connection for a bundle over T. So, and this vector field gives relations among the TI, and these relations are exactly the Ramanujan differential equations we get for Eisenstein series. So so the point is that here, if we, I mean, of course, these relations are, I mean, these functions are 3 variable functions because we are on T. I mean, they are not defined on the upper half plane or something. But the point is that we have this differential, I mean, this vector field, and the relations we get among the TIs are the same for Eisenstein series. So if you would solve these equations, like considering a derivation, for example, a derivation like Q ddq, you would get exactly the same expansion. I mean, up to constants, okay? So not exactly, but up to constants. You would get the Eisenstein series, the Q expansions for the Eisenstein series for TI. So just to be more specific, what you are doing is that you are considering T, and you have a map from T to the upper half plane, which is given by integration. So actually you consider the 2 periods of the elliptic curve, the 2 integrations over alpha. So delta 1 and delta 2 are a basis, integral basis for homology. And this is going to be positive. So this is going to be, I mean, the imaginary part is going to be positive. So this is going to be on the upper half plane. And this is how, and of course, if you could call this map phi, of course, if you consider the pullback of the Eisenstein series, you get exactly, so 2i here, the TIs here. So, I mean, that's, to be more specific, that's the relation we are getting. This is a bit more complicated than that, but I'll try to, and I mean, what happens in the Calabi-Yau case, which I'm going to explain next, is actually just a generalization of this elliptic curve example. I hope I could more or less explain this elliptic curve part. Maybe if you have questions about this you can ask. Okay, so I'll continue for the mirror quintic case. And so, I mean, the idea is pretty much the same, but first I will just give a brief review of what is a mirror quintic. So a mirror quintic, first you need to consider this family of quintics in P4, right? Given by these equations. And then you consider this group and you consider this action. So actually you are just acting by roots of unity. Of course, if you multiply here by a root of unity, you don't get anything. So, and also here, because they will multiply. So the point is that you can act on X by these roots of unity, and then you can consider the quotient. And the quotient is, and of course the quotient will be singular, so you need to resolve the singularities, and then you get the mirror quintic. In general, I mean, this is the definition, but in general, we only need to think about this equation here, because most of the things we do here will go to the quotient like pretty nicely. So, I mean, of course, we need to have the definition in mind, but many times we can just look at this equation and infer things about the mirror quintic. So let me explain now what is an enhanced mirror quintic. So of course it's the same thing as in the elliptic curve case. You consider a pair mirror quintic and a basis for the third cohomology. Of course, again, sorry, these are threefolds because they are quintics in P4, so they're dimension 3. So that's why we are considering the third algebraic cohomology. And again, we have these two conditions. The elements of the basis should respect the Hodge filtration. Oh, sorry. Hodge filtration, and also they should have constant intersection product. So it's the same thing, and a theorem like which is due to Movazati, my advisor, in 2015. He proved that the space of enhanced mirror quintics is parameterized by this open set here in the affine space. So actually here should be written like it's an open set in the affine space, okay? But I mean it's actually an affine open set, yeah. So yeah, so why is this dimension 7? I'm not gonna explain the proof in details because it's like a bit of a lengthy computation, but I'll try to explain why we have dimension 7 here. So the idea is that one dimension is for the family. So of course the mirror quintic here is a one parameter family, right? So one dimension is for this variation of the complex structure. Another dimension is for choosing. So the first, so an important thing here is that the alpha 1 here is on F3, right? So that's the same thing as saying that alpha 1 is holomorphic, right? So the second dimension is for choosing alpha 1, so a holomorphic form. And now when you're going to choose alpha 2, you have 2 dimensions, right? Because F2 F3 is 1 dimension, but F2 is 2 dimensions, right? So to choose, so you have 2 dimensions for choosing alpha 2, and for choosing alpha 3, you would have 3 dimensions, right, for choosing alpha 3, but as you have this restriction, you have that alpha 3 times alpha 2 has to be 1, right? So again, you get 2 dimensions choosing alpha 3. And for choosing alpha 4, you would have like 4 dimensions, but you have that alpha 4 times alpha 1 has to be 1, and alpha 4 times alpha 2 has to be 0, etc. So in the end, we get just 1 dimension for choosing alpha 4. So that's why we get in the end 1, 2, 4, 6, 7 dimensions, right? So that's kind of the explanation. In the next slide, I'll try to explain what exactly are these coordinates, right? So what we do is to write the equation in this form. So actually, what we are doing is that we are taking psi to the minus 5 to be equal to T4 over T0 to the 5, which is sometimes called Z also. So we are considering this. And then I mean, we get the equation like this. And we also, we write the equation like this and fix a holomorphic form. So it's more or less the same thing we did in the elliptic curve case by putting a T1 in the equation. So we are considering 2 parameters in the equation, but fixing a holomorphic form. So actually, one of these parameters is just changing the holomorphic form, not changing the equation actually, right? So that's why we have 2 parameters here, although the complex structure is just like a 1 parameter family. But we have to, but this extra parameter is for the holomorphic form. So, and then we consider, we start with this equation and a holomorphic form, and then we consider the basis given by derivation of this form. So we take derivatives with respect to this coordinate T0. If you want, this is just the Gauss-Manin connection, right? But I mean, you can abuse notation and write as a derivative, but formally this is the Gauss-Manin connection again. And then we have this basis given by derivations. Of course, this basis does not satisfy our properties, so it doesn't have a constant intersection product, and also it doesn't respect the Hodge structure. So we need to make, I mean, we need to make a change, like that there is a matrix. So of course, any basis satisfying the 2 properties we have can be obtained from this basis by a multiplication by a matrix. And the coefficients of this matrix are the coordinates Ti. Okay, so Ti are the coefficients from we use to change from this kind of like canonical basis for a basis satisfying our properties, right? So that's how we get these Ti's, but I'll not get into the details here. And okay, so the next step is to compute actually the Gauss-Manin connection. So these derivatives are easy to compute because, I mean, you just have to, I mean, it's everything pretty explicit, but we need to compute the Gauss-Manin connection matrix in these coordinates Ti, right? So what we do is that we start with this Z here, and we consider the famous paper from Candelas, De La Osa, Green, and Parks, in which they show that we have this Picard-Fuchs equation, and the solutions for this equation are exactly periods of the mirror quintic. So periods are just integrals of omega 1. So we have integrals of omega 1 and over a cycle, a 3 cycle, and this is a solution here, and we also have the integrals of omega 2, omega 3, etc. And the idea is that these derivatives here can be seen as the Gauss-Manin connection in the coordinate z, right? The Gauss-Manin connection applied to this vector field. So in the end, we get an expression for the Gauss-Manin connection of like omega 4 with respect to the, we get an expression for this Gauss-Manin connection, which is this, as a sum of some coefficients in z times omega I, right? Sorry, exactly. So actually times omega I, right? Because this is exactly what we are considering, right? So, because by definition, omega I should be the derivative of omega I plus I minus 1. So, of course, here we are considering z, and we have to make a slightly change of coordinates here to everything work, but this is just, again, a computation. And this will yield the matrix for the Gauss-Manin connection in this basis. And then using the TIs, we can change for a basis satisfying the properties. And then we are going to have the Gauss-Manin connection in the coordinates. Yeah, okay, so that's how we compute the Gauss-Manin connection in this case. We start from this equation. This equation will give us a matrix for the Gauss-Manin connection in this basis, because we have the derivatives here, so that's the basis which will appear naturally. And then by changing coordinates using matrices, we will be able to write the Gauss-Manin connection in the coordinates Ti. Okay. So the theorem which was proved is again related, a theorem related with, it's similar to the one I explained for elliptic curves. So there is a unique vector field in our space T for which the Gauss-Manin connection is of a specific form. So the important thing about this form is that if you write this in a matrix, it's going to be something like this. So 0, 0, 0, 0, 0, 0, and the rest is all zeros. So probably people from Mirror Symmetry will recall this. And it's, it's exactly the same. It's the Gauss-Manin connection. It's the Gauss-Manin connection in flat coordinates. So, but the important thing is that this is triangular. If you recall what happened in the elliptic curve, it was something like this also, right? So this is the kind of matrix we want in all these cases, right? So, this theorem is just a computation again. So after you have this T and you have the Gauss-Manin connection, you can just show that there is a unique vector field, like since you have everything explicit here, so it's it's not very complicated to show this. And then this vector field can be computed, and it's given by this very big expression. And this function y, I mean, also there's a unique vector field, and also this function y is also unique, right? For some regular function. I mean, it's any function here, and in the end, the vector field is given by this expression, and the function is given by this expression. And the point of all this is that, I mean, you have differential relations among the TIs, and if you solve these differential relations, like for a coordinate q dq, then you are gonna get these TIs written as Q expansions, right? And these are gonna have modular properties, and the interesting thing is that this Y, which appeared here, is exactly the Yukawa coupling from mirror symmetry, right? So the coefficients are counts for rational curves of degree D on a generic Quintic threefold. I mean, this is what Candelas et al. Computed in 1991. And the interesting thing is that we kind of, I mean, not this paper, I mean, it's not actually new what it's doing here, but the idea is that we now can see Y as a kind of a modular form, like a part of a more general theory, right? So we have these TIs, and Y is a polynomial in the TIs, right, or a rational function. And so yeah, so that's the interesting part of this. And also these TIs have integral coefficients in the Q expansions, right? So they also may be interesting, like in some enumerative problems. I mean, I don't know. But now I'm gonna try. So this is what happens in the closed case. And now I'm gonna explain what I did, which is the open case. So in the end, I'll try to explain why exactly we are solving this equation in a coordinate Q. Because I mean, this is kind of arbitrary, right? Because we have these differential relations, which is actually a vector field, and there's no reason for us to choose an equation, coordinate like this and solve it. So there's no reason to do this. So in the end, I'll try to explain a bit why this makes sense. And another thing which is lacking here is, I mean, I'm telling you that I'm generalizing modular forms in some sense, but what is the modular group, right? Like, where is like this modularity? So in the end, I'll try also to a bit explain this, not very much, because the idea is more geometrical, but I mean, I'll try to explain these things in the end, but if I have time, of course. But so let me now go to the open case, right? So what's different in the open case? So what we're considering? So instead of counting rational curves on the Quintic as in the closed case, we are counting disks with boundary on a Lagrangian in the Quintic. So we consider a Lagrangian in the Quintic and count disks with boundary. So the physical idea is, in some sense, like in the closed case, you don't need you don't have a boundary, so the strings are kind of closed. And in the open case, the strings need to be attached to something, and that's why you consider this boundary. I mean, I'm not a physicist, but I think that's more or less the idea. And so we have this. We want to count these disks, and what happens is that we need to consider what is mirror to this Lagrangian in the mirror Quintic. So this Lagrangian is on a general Quintic, and on the mirror Quintic we have these two conics here. So we have these two conics on the mirror quintic, and after so this is given by equations. So, I mean, you have these equations, and after acting by that group G here, here, and considering the resolution of singularities, we can see these equations are inducing two curves, rational curves, on the mirror quintic. So the idea is that instead of considering the absolute algebraic de Hahn homology, we need to consider a relative version. So we have to consider two curves, right? So instead of considering closed cycles, we have to consider also a relative cycle like this. So let me explain a bit, like recall what is the relative algebraic de Hahn homology I'm considering here. So the idea is that we have this. So if we have y inside x, right? So any closed subvariety, we can consider this. So if we call this J, we can consider, of course, the cone. So, well, we have this map, the pullback or the restriction map from x to y. If we consider the algebraic differential forms, and we could consider the cone over J star. So actually, this is the direct image here. So we can consider the cone over J star. So this should be something like this, right? The cone, again J star. Sorry. So this is the cone over J star. I mean, actually the cone is +1 here and nothing here, but let's just shift the cone like 1 by -1. And then this is our definition for the relative shift of differential forms with boundary on y. And then we can take the hypercohomology of this relative differential forms, and this is gonna be our relative de Hahn homology shift, right? So that's what we do, and I mean to define. Of course, this induces a long exact sequence in cohomology, as usual, and everything nice about relative cohomology. And also another problem is that instead of, two problems actually. So instead of a usual Hodge structure, we don't have a Hodge structure here. So what we have is a mixed Hodge structure, right? And so let me explain what is this. I mean, maybe most of you know, but just to recall. So we have two filtrations instead of just one. So a weight filtration and a Hodge filtration. And what we want is that this is increasing and this is decreasing. And the point is that if we consider like the quotients Wn by Wn minus 1, we expect that F induces a weight n Hodge structure on this quotient, right? So that's a mixed Hodge structure. And so instead of respecting the Hodge structure, our basis will have to respect like a mixed Hodge structure. And also we will have to define a relative version of the Gauss-Manin connection. But this is not really a problem because we can just do the same thing we do in the absolute case, like to define. I mean, this is not really a problem, but formally we need to do this. Yeah, okay, so after considering this, we can go to our case. So in our case, we have age 3 of x and the two curves. So this is dimension 5, right? And if we write the long exact sequence, so we are gonna get something like this. So I'm not writing the DRs here, but I mean, it's always the homology. So this is 0 because these are curves, so they don't have like higher the homologies. And so actually it's very easy to see what is the weight filtration here. So of course omega 0 is 0 and also omega 1 is 0, but W1 is 0, W0 is 0, but W2 is exactly the image of this first map. So this is important. So W2 is this image here, and of course W3 is the whole space. So notice that W3 over W2 is isomorphic to H3, so it has a weight 3 Hodge structure, and W2 is isomorphic to this image, so it has a weight 2 Hodge structure, right? And the important part also is that this image is one dimension. So the two curves here, the two generators, will be sent to the same one-dimensional space. The idea is that we have the 4 cycles coming from here, so the four elements in the basis of H3 of X, plus an extra element which comes from this homology connecting the two curves, right? So this is what's happening in homology, but in cohomology it's, I mean, the same thing. So we have an extra element coming from this H2, and the 4 elements coming from here, so that's why it's dimension 5. And if we write the Hodge filtration, I mean, I'm not gonna explain this in details, but of course F0 is dimension 5, F1 is dimension 4, because, I mean, there's one element which is not here, but F2 is dimension 2, and F3 is dimension 1. What exactly is happening here? So the idea is that we have F0 to F3 here in H3. They will be the same here, but we have this extra element. So we just have to see where this extra element goes, right? And you can compute it, and you can see that this extra element is going to be on F1, right? That's because it's like a 1-1 form, right? And that's why it's on F1. I mean, it's not, maybe it's not trivial, but it's easy to see. So that's why the F1 is dimension 4, because it has this extra element. Okay, and so again, we define this enhanced mirror quintics the same way. So we want pairs, like, I mean, here are triples because we have these two curves, so we consider mirror quintic and curve and a basis, and the point is that the basis should respect the Hodge filtration and also the weight filtration. So this alpha 0 should be in alpha 0 is the extra element, and the extra element should be in the W2 part, and the other should be in the W3 part. And alpha 0 is on F1. So that's, and also constant inner product. Notice that this element alpha 0 is degenerate because it comes from H2, so it's degenerate. And also we ask for this to be 1, and this condition is kind of strange because it seems not to be algebraic. Here, delta 0 is the homology connecting C plus and C minus. Okay, so it's not like, okay, so this condition seems not to be algebraic, but actually in the end this does not depend on the homology. So we ask this just to fix omega 0, because otherwise we would have an extra dimension of omega 0 varying, and we don't want this. So actually what we are doing here is that we are just fixing this extra element. Okay, so the theorem is that the mirror quintics can be parameterized by the affine open set given by this. It's the same idea again, so we have these 2 extra dimensions, which comes from the fact that we have 2 extra dimensions in F0 and in F4, in F1, and that's why we have 9 instead of 7. And also we use these coordinates S, and actually these coordinates are related to the coordinates from the closed case. So S0 squared is T0, or maybe you can see this like as a covering space, and S4 to the 10th is T4, right? And the others are equal, right? So this happens because, I mean, of course, these 2 spaces are related. And so we get this 9-dimensional space. Again, we have a Picard-Fuchs equation. So in the same way, Candelas et al. Show that the periods are solutions for an equation. Walcher and his collaboration show that this extra period, which is given by the integral over this homology path, this connecting the 2 curves. So the extra period is something like this. Is a solution for the inhomogeneous differential equation. So instead of considering the operator equals to 0, we will consider the operator equals to this expression, and then you have this. The solution is this extra period. So in the end, this coefficient will be the coefficient associated to this alpha 0. So associated to. So when we compute the Gauss-Manin connection, we are gonna get this coefficient will appear in the matrix, and in the end we again find a unique vector field satisfying this specific properties, and the vector field is given by this. This is square root of 5 here appears, but that's simply because there is a square root of 5 here, right? And again, the Y is the Yukawa coupling, is the same expression, and this F is the disk count. So in the end, if you again solve for QDQ, you are gonna get like physical terms. So again, we can see these physical Q expansions are inside some kind of modular form theory. And now I'll try to answer the question like why these numbers are appearing. I mean, I have 3 minutes, I guess, so I'll try to be very fast. So first, we have these actions on T and S, right? And they act by simply changing the basis alpha, because if you have a basis like satisfying these properties, of course you have a group for which when you change the basis, they still satisfy these properties, right? So these groups G are exactly this. So they preserve the intersection product and they are diagonal. So they will preserve the Hodge filtration. And I mean, then you can act. So G4 acts on T and G5 acts on S, right? And so you have these two actions, keep them in mind. And the next thing is that you can consider the period matrix. So you can look at, fix a basis for the homology. So delta I is a symplectic integral basis for homology. Of course, it cannot be symplectic in the relative case, but you just take the first one to be the homology connecting the two conics, and the other four to be symplectic bases. Okay, so you can define this period matrix, and then of course this matrix cannot be any matrix. They have restrictions. And the groups G4 and G5, as in the same way they act in T and S, they act in P, like in the period matrix by multiplication from the right. Here should be from. So this action is compatible with the period map. And also, and that's the answer for the question I raised about the modular group. There is also a left action by multiplication, which is actually changing this basis here. So these are the modular groups which are appearing, which are like subgroups of the symplectic group. So that's the modularity appearing here. But if you quotient by these two groups acting from the right, you get like fundamental domains like this. So the period matrices will always be right as this for S and this for T. Sorry, the opposite. This for S because dimension 4 and this for T. And in the end, you can show that these are dimension 1 and only depend on tau 0. And so, and also R will be exactly the derivative with respect to tau 0. So that's what I'm writing here. So the tie I will be quotients of periods and derivatives of this. And if L is the fundamental domains above, L depends only on tau 0. And this vector field will be the vector field R. So in the end, L makes the same role as the modular, the upper half plane. R plays the same role as the Ramanujan equations among the Eisenstein series, E2K. The TIs are the Eisenstein series, and that symplectic group there will be the SL2 here, right? So that's the way that's the sense in which we are generalizing modular forms. And also if you consider tau 0, the coordinate Q we were using here is exactly the exponential of tau 0, or maybe 2 pi I or something. And this is also very standard in physics, which is the mirror map, right? So to end, I mean, I'm over time, but just 3 quick questions which are still open. So what happens in general, like for general Calabi-Yau? So we are considering the mirror quintic here, but can we prove something in general? Because here everything is very explicit and computable. But can we make like a more general theory of modular forms in this way? What kind of generation functions we would get in this case? Is it related to physics? Is the moduli space in the first place, is it quasi-affine or not? So all these are kind of open. So another idea is to consider a moving family inside X, not only a fixed family. And this should give us like a generalization of Jacobi form. So there would be two variables. And also, this is interesting physically. I mean, there are articles in which the physicists derive Picard-Fuchs equations in this case. So this may be very interesting. And also, maybe we could consider other cases in which we have mixed Hodge structures, for example, singular varieties. Okay, so that's all. Thank you very much.